theorem. If A is invertible n by n matrix, then Ax equals to B has the unique solution for every choice of B from Rn. It follows from the fact which we observed earlier, if A of x equals to B, then A inverse Ax equals to A inverse B, then x equals to A inverse B, because A inverse times A is identity matrix times x is x, and we have our unique solution that x is supposed to be equal to A inverse of B. Matrices. I'll show a few examples of elementary matrices on 3x3, an example of 3x3 matrix. For example, if I have matrix A, which is, say, A11, A12, A13, A21, A22, A23, A31, A32, A33, then I can define what E3 elementary matrix is. So it's basically almost your identity matrix. The only catch is instead of 1, we have 5 or something like that on the main diagonal, the third element on the third row. And now if we take E3 and multiply by A, if we do operations, what we're going to see that is going to be, it's because row 1, row 2 are unchanged, we only changed from identity matrix to row 3, so when you do multiplication, that implies that our first two rows are not going to be changed in the multiplication. Because row 3 only participated in them when we do multiplication by for row 3 in the end result. And because we have 5 here, so the third row becomes 5 times of original one. Okay. So what that matrix does, that elementary matrix E3 does, it kind of tells us that we can multiply by a row by a number. Elementary matrix of a second kind looks like this. So what is going on here is it's basically your identity matrix, but it's row 1 and row 2 flipped. So it's row 1 and row 2 flipped. And if you take E2 and multiply by matrix A, what is going to be happening? We do multiplication, we carry it out. Then the row 3 are not going to be changed. But row 2 and row 1 are going to be switched. E2 and A2, 3. So switches row. So E2 switches row, E3 multiply row by number, and E1, for example, I'll write down 1, 0, 0, 0, 1, 0, 0, 3, 2, 1. And if I'll multiply it, what is going to be happening? Row 1 will stay the same. Multiply the matrix A. Row 2 will stay the same. But row 3 becomes the sum of row 2 and row 3. So we're going to get A31 plus 2A21, A32 plus 2A22, A33 plus 2A23. So what is happening is every elementary row operation which are multiplying a row by number, switching rows, or adding row multiplied by number to the original row, they can be expressed as a product of your matrix by your elementary matrix. That's the first observation. Second observation, matrices E1, E2, and E3 are invertible. So, for example, to invert E3, you multiply by E3. To multiply E3, you multiply by row operation where you multiply it by 1/5, the third row. To undo E2, you do E2 again, you switch row 1 and row 2 again. To undo E1, you do subtract row 2 from row 2 from row 3. Okay, so for example, E3 inverse is going to be 1, 1, and 1/5 here. The rest are zeros. E2 inverse are going to be E2 itself, and E1 inverse is going to be 1, 0, 0, 0, 1, 0, 0, minus 2, 1. So instead of adding, you subtract 2 row 2. If I start with matrix A, I'll start making row operations to it, and eventually I can get to identity matrix. Okay. By doing row operations. By previous observation, doing a row operation is equivalent to multiplying by elementary matrix. So what is going to be happening is we have A, then from A, by doing a row operation, we got E1A, then we got E2 times E1A, and so on. So eventually we get EK E1A equals to our identity matrix. So after doing k row operations, we get identity matrix. So from here we can get, if we look at the last identity which is written here, k dot E1A equals to identity matrix. So from here, inverse of EK times E1 times A equals to EK times E1 inverse. So A equals to EK dot E1 inverse, from which we conclude that A inverse equals to inverse of right side. Double inverse is our original matrix, from which we obtain algorithm how we're going to be finding inverse matrix. So to find inverse matrix, we'll do the following. We start with A, and we're going to write down identity matrix to it. Then we start doing row operations. To that big matrix. And our goal is to get identity matrix by doing row operation to A. And if we succeed, if we can get identity from matrix from A, then IN becomes A inverse. If we are not successful, then if we cannot get identity matrix by row operation from A, then A will not have inverse matrix. So let me do an example or two. Find the inverse of 1 minus 2, 1, 4 minus 7, 3, minus 2, 6, 4. Start writing 1 minus 2, 1, 4 minus 7, 3, negative 2, 6, 4. We write an identity matrix next to it. Then we want to get firstly echelon form. So we do row 2 minus 4 row 1 and row 3 plus 2 row 1. So if we do that, we're going to get 1 minus 2, 1, 1, 0, 0. So row 1 is not changing. 0, 1 minus 1, negative 4, 1, 0 for the second one. Third one becomes 0, 2 minus 2, 2, 0, 1. And then we do row 3 minus 2 row 2, 1 minus 2, 1, 1, 0, 0, 0, 1 minus 1, negative 4, 1, 0, 0, 0, 0. And I'll stop here. I don't even need to do any over calculations because I see row of zeros, and there is no way I can get identity matrix if I have row of zeros by doing row operation. So we conclude the matrix is not invertible. Okay, next example. Find the inverse matrix of 1, 0 minus 2, 3, 1 minus 2, negative 5, 1, 9. So we're going to write down 1, 0 minus 2, 3, 1 minus 2, negative 5, 1, 9, identity matrix next to it. Then we want to get reduced echelon, firstly echelon matrix, so row 2 minus 3, row 1, row 3 plus 5, row 1, so we're going to get 1, 0 minus 2, row 1 is not changing, 1, 0, 0, row 2, 0, 1, 4, negative 3, 1, 0, 0, negative 1, negative 1, 5, 0, 1. So we have row 3 plus row 2. Row 1 and row 2 are not changing. We're going to get 0, 0, negative 1 plus 4 is 3. 2, 1, 1. we divide row 3 by 3. So we're going to get 1, 0, minus 2, 1, 0, 0, 0, 1, 4, minus 3, 1, 0, 0, 0, 1, divided by 3, 2/3, 1/3, and 1/3. And then all that is left is to take care of it for -2. So we do row 2 minus 4 row 3, and row 1 plus 2 row 1. So we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. So matrix A becomes identity. 2/3, 1/3, 1/3. Last row is not changing. Row 2 minus 4 row 3. -17/3. -1/3. -4/3. 7/3. 2/3. 2/3, because multiplying by 2. So from here we get A inverse equals 7/3, 2/3, 2/3, -17/3, -1/3, -4/3, 2/3, 1/3, and 1/3. And probably worth taking 1/3 out, and the answer will look a little bit better. 7, 2, 2, -17, -1, -4, 2, 1, 1.